Alright, so let's start solving the exercises on inner product spaces. And in this first one, we have F as the field of real numbers, and on this we have the vector space V, which is just the 3D space over F consisting of all the ordered triples of real numbers. That is ordered sets with 3 coordinates. We have to show that the cosine of an angle is of absolute value at most 1 by using the Schwarz inequality in this vector space. Okay, this is a fact that we already know from trigonometry, and we have to derive it from Schwarz inequality. So let's see how that can be done. So we need to show that the absolute value of cos theta, where theta is any real number, is at most 1. That means less than or equal to 1. So let us start the solution by considering any real number theta. And now we are going to consider 2 vectors in our vector space, one of which is this cos 2 theta comma sin 2 theta comma 0. Keep in mind that these vectors have to be ordered triples of real numbers. These are of course real numbers, and the other one is cos theta comma sin theta comma 0 in V. Now our aim is to show that the absolute value of cos theta is less than or equal to 1. So let's consider the absolute value of cos theta. Now is obviously equal to the absolute value of the cosine of 2 theta minus theta. Now we are going to apply the addition formula for cosine. Although you have minus here, but still it is the sum of 2 theta and minus theta. So in that sense, addition formula, which is cos 2 theta cos theta plus sin 2 theta sin theta. In case of cosine, in case of sine, if you have plus here, then you have plus here. If you have minus here, then you have minus here. But for cosine, that's opposite. Now, if you look carefully at this absolute value, this is nothing but the absolute value of the inner product of u and v. Because what is the inner product? You have to multiply the corresponding components in these vectors and take the sum of those products. So cos 2 theta cos theta that you have here, plus sin 2 theta sin theta, you have that here, plus 0 times 0, that will not be there, it will vanish. So that's why this is the absolute value of the inner product of u and v, and this is where we can use Schwarz inequality. So by Schwarz inequality, this is less than or equal to the product of the length of u and the length of v. But if you calculate the length of u, what will it be? That's just simply the square root of cos square 2 theta plus sin square 2 theta plus 0 square, which is 1. Similarly, the length of v is also 1. So that means this is nothing but 1 times 1, which is equal to 1. So that's how the absolute value of cos theta is at most 1. Okay, so we have derived it as a consequence of this Schwarz inequality on a vector space. So that's the solution. Let's see the next one. Number 2. Again, if f is the real field find all four tuples of real numbers. A, B, C, D, such that for U equal to alpha 1 comma alpha 2 and V equal to, let me erase this part, and for V equal to beta 1 comma beta 2. That means these are two vectors in F2, the two-dimensional vector space over F. Yeah. For these two vectors, we are now going to define a function which looks like an inner product because there are two inputs. One of them is U and the other one is V. And the function is defined like this: A alpha 1 beta 1 plus B alpha 2 beta 2 plus C alpha 1 beta 2 plus D alpha 2 beta 1. Now before we complete this, you note that this actually is a function of what kind? It's a function from this Cartesian product into F. So it's the type of function that can be an inner product, right? Because you are taking two vectors and as a the value is a real number. Now the question is this, that we have to find all those four tuples of numbers. That means we have to find four real numbers for which this becomes an inner product. Defines an inner product on F2. So let's see what we can do. Our plan is to first of all assume that this is an inner product, and then we will try to see what restrictions we get on this A, B, C and D. From that we will try to guess what the A, B, C and D can be. Okay, and then we will have to show that for such A, B, C and D, actually this becomes an inner product. Okay, so that's our plan. So let's see how it goes. For in F, let the given function be an inner product on F2. Okay. Now we are going to give some names to some vectors. Let E1, that is, we are going to name the standard basis vectors in F2. One of them will be E1 and the other will be E2. let E1 be 1 comma 0 and E2 be 0 comma 1. Then for our u and v, anyway, let's just once again write for u equal to alpha 1 comma alpha 2 and p equal to beta 1 comma beta 2, need to write that they are coming from f2. In f2 we have, okay, so now we are going to calculate the inner product of u and v, not using this formula but using the axioms for an inner product, because you see our assumption now is that it is an inner product. So so that means we can apply all the axioms that are there in the definition of an inner product. So that way, if we try to calculate the inner product of u and v, what do we get? We then get this. So what we first do, we express each of these two vectors as a linear combination of the basis vectors. You know how. Okay, since u is alpha 1 comma alpha 2, so it can be written as alpha 1 e1 plus alpha 2 e2. Similarly, v is beta 1 e1 plus beta 2 e2. Now we use the axiom that is that gives us linearity of inner product in both the variables. You see, actually we get conjugate linearity in one of the variables, but because we are in a vector space over the field of real numbers, it's a real vector space, so we get linearity in both the components. What that ultimately means is that if you use linearity, you will end up having this. You can, I'm going to skip one or two steps and just directly write this. You will understand what I have done here. Alpha 1 beta 1 times the inner product of E1 and E1 plus alpha 2 beta 2 times the inner product of E2 and E2 plus alpha 1 beta 2 times the inner product of E1 and E2 plus alpha 2 beta 1 times the inner product of E2 and E1. Okay. So what do we get? But at the same time, this is also equal to this. So A alpha 1 beta 1 plus B alpha 2 beta 2 plus C alpha 1 beta 2 plus D alpha 2 beta 1 is equal to E11 alpha 1 beta 1. We can of course write this in this way because these are after all real numbers, plus E2 comma E2 times alpha 2 beta 2 plus E1 comma E2 times alpha 1 beta 2 plus E2 comma E1 times alpha 2 beta 1. Now note one thing, that this U and V actually are our choice. So we can choose any vectors in place of them. And now we are going to cleverly choose some vectors so that we can establish some relationships among these things, among the A, B, C, D and these inner products between EI and EJ. Taking alpha 1 equal to beta 1 equal to 1 and alpha 2 equal to beta 2 equal to 0, we can do that. Okay, that means considering which vectors. U is 1 comma 1 and V is 0 comma 0. For these two vectors, we get what from this equation? See, alpha 2 and beta 2 are both 0. So this term would vanish in the left hand side. This term would vanish. This would vanish because beta 2 is 0. This would also vanish because alpha 2 is 0. Only this one will survive. And because of alpha 1 and beta 1 both being 1, this one will be A. Similarly, on this side, we will have only E1 comma E1. So we get this. But now, similarly, other choices can be made. For example, taking the exact opposite thing, alpha 1 equal to beta 1 equal to 0 and alpha 2 equal to beta 2 equal to 1, you will see that in that case we get B equal to E2 comma E2. Let's see how. Alpha 1 and beta 1 are 0. So this will vanish. This will vanish because of alpha 1 and this will vanish because of beta 1. And this will be B. Similarly, on this side, we will only have E2 comma E2. So that gives us this. Similarly, for appropriate choices for alpha 1, beta 1, alpha 2 and beta 2, we are not going to say what those choices are. You can understand. We are going to get these things also. C equal to E1 comma E2 and D is equal to E2 comma E1. Okay, note that okay, what have we done here? Let us summarize. The function originally is already given in terms of A, B, C, D and the components of the vectors. But now we have assumed, that's where we started our thing, that the function is an inner product and we are getting these relationships. And now these relationships are going to tell us some things about this A, B, C and D. Note that because each one of them has been found to be some inner product values now. Now, what kind of consequences can we have from these relations? First of all, note that A is this inner product. Now we know what this inner product is. What this inner product is means, oh, and one more thing, keep in mind, this is not the standard inner product on R2. No, it may not be because it is given in terms of A, B, C and D. It can be any on R2 or on F2. There we don't have just one inner product. There may be many functions which are actual legitimate inner products. So this is one of them. We don't know which one it is. So you cannot use any definition for this inner product here. We don't know, we just know that it's an inner product, so it will have some value, but we still know something about it. Namely, that whenever you have two vectors in any vector space, any inner product space, and you take this vector u prime and find its inner product with itself, we know that this is always a non-negative real number, and it is equal to 0 if and only if the vector u prime itself is 0, that is non-degeneracy. Here also we have the same situation, but is the vector e1 0? No, it's a basis vector, how can it be 0? So that means A has to be positive, A is strictly positive. Similarly, B is also positive. What else can we say? C is equal to D, because we are in a real inner product space, so it does not matter if you change the order of the vectors in the inner product function. So now we are going to write these conclusions. So note that this is positive, B equal to E2, E2 is positive, C equal to E1, E2 is also equal to E2, E1, which is equal to D, and something else can also be said. We can also link A, B and C, and that can be done via the Schwarz inequality, and it actually comes like this. Here, AB is E1, E1 times E2, E2, that is the square of the length of E1 times the square of the length of E2. Why? Because the length of E1 is the square root, non-negative square root of the inner product of E1 with itself. So that's why we have this. But then by Schwarz inequality, this is greater than or equal to the absolute value of the inner product of E1 and E2. Square, of course, it's square, which is C square. Because our inner products are giving us real values, complex values of course, but they are real numbers, so we can get rid of the absolute value sign. Absolute value of C square is equal to C square. That is only true for real numbers, okay? So that's why we have C square here. So these are some things that we have come to know are true about A, B, C and D. So what are the things? A and B are positive, C is equal to D, and AB is greater than or equal to C square. Now what happens if AB is equal to C square? Let's see. Suppose AB is equal to C square. Then we are going to calculate a very particular, a special inner product, and that is the inner product between these two vectors, same vector, minus C over A times E1 plus E2. What do we get? Let's just apply the definition. Well, okay, what should we do? Should we apply the definition itself, or? Yeah, I think we can apply the definition of this function itself. No, that way it will be quicker. So what is this vector? It is just minus c over a comma 1, and this same thing, minus c over a comma 1. So what is the definition of this function? A times alpha 1 beta 1. In this case, alpha 1 and beta 1 are the same and they are equal to this. That means this plus b times alpha 2 beta 2, both of which are 1, plus c times alpha 1 beta 2, that is this one times this one, that means minus c over a, plus, because d is again c times alpha 2 beta 1, again same thing. Okay, so what do we get? Remember, we are calculating this under the supposition that AB is equal to C square. Okay, now 1A will get cancelled, so we will be left with C square over A plus B, okay, minus c square over a minus another c square over a, that is b minus c square over a. So you can see that this actually becomes 0, right? So this inner product value is 0, and when the inner product of a vector with itself is 0, then that vector has to be 0. That is one of the axioms in the definition of an inner product. So this implies that minus c over a times e1 plus e2 has to be equal to 0, or E2 has to be minus c over a times E1, but this is not possible since E1 and E2 are linearly independent, and in fact they form a basis for our vector space. So how can they satisfy such a relation? They cannot be scalar multiples of each other. That means our supposition is wrong. So AB cannot be equal to E square. AB has to be strictly greater than C square. So that is an extra condition that we have come to know about the relationship between A, B and C. So our last supposition is wrong, i.e. we must have AB strictly greater than C square. Okay, so far what are the things on A, B, C and D? A and B are positive, C is equal to D, and AB is strictly greater than C square. And that's it. Now we have to do the converse. The converse is this. We are going to assume that we have our function which looks like an inner product, but now we will assume that these conditions are there linking A, B, C and D, and we will prove that as a consequence of that the function becomes an inner product. Okay, so these are not just necessarily true for the function to be inner product, but they are also sufficient so that when they are true the function becomes an inner product. Conversely, let A, B, C and D be real numbers such that A and B are positive, C is equal to D, and AB is greater than C squared. We define U comma V for U and V in F2 as given in the exercise. That means using A, B, C and D in that way. Now this function definitely has the form of an inner product. That is, it maps the Cartesian product of F2 with itself into F. So now we have to verify the axioms one by one. Okay, let's see. Let which one have I verified first? I cannot think straight because of extreme heat actually. It's really very hot and it's getting even hotter. Oh, but before we do these things, it would be helpful if we write the form of the function, because C is equal to D. So let's just write it. Under these conditions, we have U comma V equal to, again, A alpha 1 beta 1 plus B alpha 2 beta 2, but because of equality of C and D we get this beta 1, where U is alpha 1 comma alpha 2 and V is beta 1 comma beta 2, and they are coming from F2. So what is it that we first should show? We should first of all show that this is greater than or equal to 0 and this is equal to 0 if and only if U is equal to 0. One thing that is obvious in this case is that no matter what the vectors are actually, not just in this case but for any U and V, the inner product values are in fact all real numbers. That should not be taken lightly, because in the general definition of an inner product, where the underlying field can be the field of complex numbers also, there this condition holds the meaning that u comma u is not just a real number but in fact a non-negative real number. Now this being a real number in general is not trivial for a general inner product space, but because we are dealing with real inner product space, it's real number. Okay, always it's real number even when u and v are not equal. Okay, so that is fine. So now what we should do, we should in fact show this. Actually showing these things is equivalent to showing this. That is one thing. And if u is not equal to 0, then this is strictly greater than 0. That's just it. If we are able to show these things, then we have shown these things. Okay, obviously this is equal to 0. Why? That's because if you think of u here, okay, if our u is 0, then alpha 1 and alpha 2 are both 0, right? So if alpha 1 and alpha 2 are both 0, then this is 0, this is 0, and here also these are also 0, so we get 0. Now let u be not equal to 0. So that means at least one component of u is non-zero. We are going to assume that alpha 1 is non-zero, and in fact without loss of generality, we assume that alpha 1 is not equal to 0. Actually, I am not exactly sure if I should write without loss of generality, because alpha 2 being non-zero is really another case, but that other case is so similar to this one that I am using this language. And now let me just use some ink also, because I think I am running out. Because of this heat, things are drying up also very quickly. Okay, then we are now going to calculate u comma u. What will be u comma u? Because alpha 1 is equal to beta 1, so this is a alpha 1 square. Similarly, beta 2 is equal to alpha 2, so b alpha 2 square. And here you will get alpha 1 alpha 2, again alpha 1 alpha 2. So 2c alpha 1 alpha 2. Okay. Now a is already non-zero, and in fact a is positive. That was our supposition, our hypothesis in this part of the solution. And now because alpha 1 is non-zero, so its square is also non-zero. So what we can do is we can take a alpha 1 square common out. We will then be left with this 2c alpha 2 over a alpha 1. Now we are going to complete a square inside. You know what that means. For completing a square, we already have one term that can be written as a square, alpha 2 over square root of a alpha 1 whole square. Note one thing carefully, that because we have assumed both a and b to be positive real numbers, so there is no problem with this. Plus 2 times this, if we write, but originally what we had this, so that means it will be c over square root of a. Is it coming? Let's see. Square root of a times square root of a is a in the denominator. We have alpha 1 also. Square root of b and square root of b cancel out, and we have c alpha 2 in the numerator along with 2. Fine. Plus c square over ab, that's the square of this term, so that we have written extra. There was already one plus 1, so minus c square over ab. So what does it become? It becomes this, alpha 2 over this alpha 1 plus c over square root of ab whole square. Okay, so that taking this and this term, so outside we still have this, and here if you still change things a little bit, you get this. Now it is in a very nice form. Let's see in what form. This term, that is the square, is non-negative. It cannot be negative. It's either 0 or positive. A is positive. Alpha 1 is non-zero, and so alpha 1 square is positive. A and b are both positive, so here the denominator is positive, and because we have assumed ab to be strictly greater than c square, so the numerator is also positive. Everything is positive here. No question of having negative, so this is greater than 0. So that's how, if u is non-zero, then this our function actually gives us a positive value. So one property has been satisfied. What else do we have to show? We have to show that what is that thing called? Conjugate symmetry. In this case is just symmetry, because we are in a real vector space. Also, this is equal to v comma u, and that can be seen quite easily why that happens, because the function is symmetric about the components of the vectors. Yeah, that's just the thing. Now finally we have to show linearity, and linearity, linearity actually we need not worry about complex numbers and those things. Yeah, so we just show ordinary linearity in this component, the first component, and that's just it. Finally, let's consider another vector gamma 1 comma gamma 2 in F2, and we would need to scale ourselves. So alpha and beta in F, we have, what is it that we are going to calculate? Alpha u plus beta v and w, the inner product of these two things. Okay. So for our own understanding, so that we don't make any mistakes. Let's just actually write these things now. What will this vector be? U is alpha 1 comma alpha 2 and V is beta 1 comma beta 2. So alpha alpha 1 plus beta beta 1 comma alpha alpha 2 plus beta beta 2. This is alpha U plus beta V comma W is gamma 1 comma gamma 2. Right. So now we use the definition of this function. A alpha 1 beta 1, that means A times the first coordinate here times the first coordinate here gamma 1 plus B times second coordinate beta beta 2 times gamma 2 plus C times the first coordinate of the first and the second coordinate of the second. Well, we do not have D. I mean, we have D, but that is just C. So C times alpha alpha 1 plus beta beta. It's very easy to get confused. This times gamma 2 and again C times the second coordinate of this one, that is alpha alpha 2 plus beta beta 2 times the first coordinate of the second, that is gamma 1. Now if we look carefully, there are some terms from which we can take alpha common out. This is one of them. And if we take alpha common out actually, then the other term will be A alpha 1 gamma 1. Do you see this? A alpha 1 gamma 1. We are taking this alpha outside. Plus, from this one also we can take one alpha out. B alpha 2 gamma 2. Plus, from this one we can take one alpha out. C alpha 1 gamma 2 plus from this one again C alpha 2 gamma 1, and just like that from the all the second terms we can take one beta common out. So doing that we are left with A beta 1 gamma 1 plus B beta 2 gamma 2 plus C beta 1 gamma 2 plus C beta 2 gamma 1. And we can see that this first thing within parenthesis is nothing but the functional value of this function where we have U and W. I am still not saying inner product because we are showing that, right? Plus beta times, and this one is V comma W. So that's it. So now we have shown linearity. Hence, the function above is an inner product on F2. So those conditions on A, B, C and D, let's just once more recall them. A and B have to be positive, C must be equal to D, and AB has to be greater than C square. So they together they give us a necessary and sufficient list of conditions so that that function becomes an inner product. that function becoming an inner product and these conditions being true are equivalent to each other. Okay, so this is where the solution ends. And let me just end this video here itself. Tomorrow we have again our next upload, and tomorrow what shall we do? We have already once more gone through Lee's algebra exercises, so tomorrow let us again solve which one should I do, groups or doing groups. Let's do group exercises from Galilean. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.